back down to a more immediate level, 6 months to 3 years out. That's that future state discussion at a value stream level. And again, how many of us have done value stream mapping? Okay, so we get that part, right? Before, and when Brandon and I went to hear Mike speak, I had a really hard time because I was traditionally following what I thought was the way he wanted us to do it. We do our current state map, right? And then we did our future state map, and then we came up with a big list of action items, and we just knuckled down and worked on it. What he said is we don't do that anymore, right? All we do is we start with one. We go our current state map, we predict the future state map, and then we pick one obstacle. And after we've worked on that, we step back and say what's happened, what changed, and from that answer we decided what to work on next. To me, that was like, wow, what a weight lifted off my shoulders, you know, to boil the ocean. I can do it one piece at a time. Anybody done this before where you've kind of made the current state, future state map and made the big list? Anybody done that? And does it instinctively tell you, are we really supposed to be working on this, or should we be doing something else? Well, we do it because we feel like we have to, right? Again, we're not so sure back then, was that really purpose-driven activity? This is what this is trying to do for us. All right, so now we're going to take a look at the next piece. We're going to look at the current condition. So there's a lot of information here. We have a discrete manufacturing process, 6 steps in the process. We're putting springs in the board, we're putting resistors, green and red, we're putting diodes in, we're putting LEDs in, and we're testing. We have a certain information here so we can calculate. We know that we have a takt time about 12 seconds. That's what we like to have, but we don't know what we have right now. So we need to go and look at the current condition. So again, we've set the direction, talked about vision and challenge. With that, we understood what we needed to do, and now we're going to go and say, what is the current pattern of work? What does that thing look like? How do we describe it? So why are we doing this? The purpose is not to go in that waste wall, not to uncover problems or waste or potential improvements. It's simply done to obtain facts and data that we need in order to describe the target condition. So we don't need to spend a whole lot of time coming up with that information. We don't know what to work on until we have established that target condition. And that becomes the benchmark against which we do our purpose-driven activity. Once we have a target condition and we strive to move forward, by using these PDCA cycles, we begin to discover what's next. So the path, although we don't know, it manifests itself one step at a time. So grasping that initial condition is a step toward establishing, again, the first target condition. As we're ready to establish the second target condition, we go through the same process. We'll learn a lot more about it, and these cycles become much easier. So again, the process analysis for that second and subsequent target condition proceeds a lot quicker. So here's a little 5-step visual look at how this thing goes about. On the left-hand side, sort of have a generic understanding of what we're trying to do. And one of the things that Roth has done for us in his book is he's kind of described a discrete manufacturer. But he's also encouraging us to think beyond that. It could work in could work in the office, could work in maintenance, could work in warehouse, could work in healthcare. We're just looking for what is that pattern of operation now, what would we like it to be in the future. So he's got 5 steps here. Customer demand to plan cycle time. In other words, what's the task unit, and how much time do we have to complete it, right? Over here, for a discrete manufacturer, we begin to talk about takt time, plan cycle time, and how many shifts we're running. Next, we kind of look at the characteristics of the process. How can we describe it? Can we sketch it? Can we come up with process metrics? We're going to do a little bit more here in a second. I'll go to another slide, kind of explains to that. But we go through customer, characteristics of the process, talk about the equipment. If we've got equipment in there, it could be a constriction. How many people do we actually need to have? And then what's the outcome metrics? How is the process currently performing over time? So let's begin to look at these things one at a time. Again, customer demand and plan cycle time. We're talking about takt time. Who doesn't understand takt time? Everybody okay with that? Maurice, anybody else? Okay, it's just the heartbeat of the customer, right? It's the tempo. We need to know what that cadence is. Again, if we have a discrete manufacturer where we're making things like that, it's easy to come up with. If we're making airplanes or for job shops, it's a little bit different. But where we can, we want to utilize and calculate takt time. Once we know that, then we can come figure out planned cycle time and how many shifts we're running. So again, for example, we went to Toyota back in early 2000, and they had a 55-second takt time, Georgetown, okay? Means that every 55 seconds a brand new car was coming off the line. It also means that every workstation had how many seconds to do their work? 55 seconds or less, right? So they didn't design the work content exactly for takt time, they did it something less. And that's where the planned cycle time comes in. It takes into consideration a little of the downtime and some of the efficiency. So that takt time, that pace is what we're looking for where it's available. So, customer takt and planned cycle time. Again, this top line here on the graph, is what we're going to see, is what we call takt time, and that is the customer demand rate. Okay? Beyond that, or below that, is the planned cycle time. We want to try to be able to reach that plateau, be able to operate a balanced line. It's a little faster than takt time to accommodate these things that have to do with changeover and some downtime. Again, initially any planned cycle time or takt time numbers we come up with might be wrong. It's okay. It's good enough for start. Okay? So here's an example of how we go about doing this. Okay? The formula is simply how much time do we have available through our work time to operate. Take out breaks and lunches and, or other things. And then during that period of time, whether it's on a shift or a daily basis, how many units we get from it. So this gives us a picture of the rate of the customer demand against which we then need to build our process. And if we can't meet customer demand, we're going to be late or we're going to be working overtime. We know that drill. So here's an example, 26,100 seconds divided by 450 units. You do the math. And in this particular process, they have to have a 58-second takt time, so they have to build their process to meet that customer demand. We know that demand changes. We want to look at that number as often as we need to. How many of you actually run to takt time now? Tony? Great. Jeff, you too? Great. How's that working for you?
Works out well.
Yeah.
Let you know when you have a problem really quickly.
Okay. So how many of you could work to takt time if, you know, it's available, right? And if you aren't designing your process to meet takt time, what happens? Overtime maybe? Misshippers, things like that? So,
I mean, like Bill's saying, some of y'all are working to takt time. Other folks, have you calculated takt time, you're just not achieving it, or you don't even have that as the target? Just a little feedback.
I think for the McKee group, it's hard to, because of our continuous process, but when we have a batch time, we have a set allowable batch time. So for us, that would be takt time.
Okay, so many batches per shift.
You have so many minutes per cases on, you know, theoretical takt time.
yeah.
We have takt time, but the decisions being made in the line is not based on the takt time, it's based on sales. So takt time tends to sort of, you know, take a back seat and the sales end.
So Joe, how does sales factors into that, right? This is really sales. The quantity the customer requires, isn't that sales? So the number's there, but you're not really...
Well, what happens is, you know, you have your machine problems and absenteeism and meetings and different things like that. And
Okay.
so then all of a sudden, you know, you're behind.
Okay.
I think so you have your target as takt time, but at your adjustments, okay.
Yeah, it's hard to maintain it and stay on that course.
If you have that out there as a target, so you
Yeah.
understand that you're not meeting it.
Yep.
And we have the fund where, you know, we're doing multiple products per line. It's usually, you know, bottles or cases.
Okay.
So they all have different takt times. You know, takt time on a bottle might be 25 milliseconds.
Okay.
You're doing, so we just go in how many units per minute. And then we also get the counter problem where our takt time isn't necessarily aligned to customer buying habits because we still have some influence of forecast.
Okay.
The plant a lot of times just ignores the forecast and looks at the actual orders coming in, but they're still being driven and expected to perform to some of the forecast models.
Yeah, well, like I said, that demand number is, you know, it has typically estimated somehow.
We know the cycle time is just how often does the piece fall off the line. It's not necessarily the same thing as takt time, because it may not be falling off fast enough to meet takt time. So, any comments, questions? Maurice?
VSO repeat. And we do 8 feet a day.
Okay.
And we don't, and we had always problems because the customers always came at the end of the day.
Okay,
So we analyze this as well, and we know now which product they always, they ask. What we do now, we build already in the morning, we know as for
okay,
so that the pressure is off in the afternoon,
okay.
so that then you get the pressure off at the end of the day.
Okay, so your order pattern changes throughout the day, and all of a sudden you've got an
And you split
end
it
of
out.
day crisis, right?
Yeah.
Anybody deal with that before? You know, it really
Yeah,
disturbs things.
we have a lot of
Understand, right,
discussion
Joe?
about how to handle make the stock versus make the order demand.
Right.
And how to plan the day. Because within a day, a process needs to serve both customers. It needs to serve make the stock product that's gonna be in distribution, and then there's orders, there's a backlog of orders, not all of them, for make the order need to be done today. But some of them do. So we have a lot of discussion about how to plan. Really, essentially, you're planning two different ways to run every day. Production plan over time, your stock products, that tack time should be more stable. You should plan your process to run, or plan a cycle time to run to that tack. But then after you're finished with that part of your schedule, then how do you operate the line for the make the order demand? Because it's a different profile.
So what you're describing from Maurice, what you heard Garvin saying is that designed to tack time, but also capable of maybe adapting to these last minute daily changes, that kind of thing?
Yeah.
Is this a normal pattern every day for you?
Yes, what we do is we build for 1 week of stock, only 1 week of stock, and only on the fast moving products.
Okay,
What you get then is that the whole process will go faster, because the order picks don't have to wait on the feet that are already built, we can proceed. So the whole process goes faster, and what we achieved is that we didn't do any overtime anymore.
so like Garvin said, if you can design to the worst case scenario, somebody?
And it's interesting, for a long time, we considered to make the stock more important because it drove a metric, right? You get all these make the stock line items, you're gonna have a great on-time service metric. The pure math of the make the order would never affect that metric. And we had I guess a strategy shift that says, make the order is a customer now, make the stock is a customer later. So now we prioritize make the order first, have a window during the day in most processes to do that first. And we plan an amount of time for make the stock. And if the make the order window needs to be larger because of demand, then you extend the day, or later in the week, extend the week. You're still running your make the stock to the same tack rate, the same quantity. That's a long-term plan. You're just adjusting where it fits in your weekly schedule.
Makes sense? So, you know, we're trying to create a model, one size fits all, hard to do, but like Garvin said, if we can satisfy customer needs first, then we can, just, you know, like your situation where the dynamics change so much you don't have control. You know what your tap time is, but you just, you know, at this point, don't have the wherewithal, right?
I mean, sometimes, because one line may be having trouble, your customer demand in your line is 100, because that other line is having trouble, well, let's try to get 150 out on your line this month.
We can get out of that tournament.
The customer, you got your customer requirement, then you got your, what I call the productivity coordinator's requirements. You throw that at you.
So again, tack time is an important concept. We want to try to build up process to meet that where we can. Yeah. All right, so talk about planned cycle time. If you know the changeover times and the downtime, back them out. It's as simple as that. If you don't know what Rother says, make it easy. Just take 15% off your tack time and try to design to maybe 85% of your planned cycle time. It's just a start, right? We're allowing for a little bit of that difference there where we have to deal with changeovers and other losses. So here's an example of a tack time calculation. We have a process that has to make 1,840 pieces a day, right? We've got 2 shifts, 8 hours each, 2 10-minute breaks per shift, 10 changeovers a day at 15 minutes each. We've got a little bit of reliability issue here. We have about 10% downtime. So again, look at tack time and planned cycle time. If we take 2 shifts times 8 hours times 60, we get 960 minutes total available. We're backing out the breaks, 40 minutes a day for the breaks. And that leaves us 920 available time, right? Multiply it by 60 seconds, you get 52,000 divided by the 1840, and we got about a 30-second takt time. If we designed our process capability to that, it would be hard because we know stuff happens, right? What did Art say yesterday in manufacturing? Something happened, right? So we look at planned cycle time, we say, all right, let's start with available time, and now let's back out the time for the changeovers, 10 of them at 15 minutes each. And that now brings us down to only 770 minutes. And we've got a little reliability issue here, about 10%. So let's take that out. So it's not that we're penalizing ourselves, but we're dealing with reality at this point, saying that we really only have 693 minutes available because of this other stuff. So at that starting point, our planned cycle time then needs to be 41,580 divided by 1840, or 22.6%. That's about 75% of your takt time, as opposed to 85. So whether you do it knowing your downtime, your changeover, or just start with 85%, doesn't matter. But again, we kind of bring that level down so we can let you take into consideration those inefficiencies. Step 2 then is let's look at the process. What do we want to do here? We want to get to know the process. We sketch it. We want to see how does the process fluctuate. We know it's not going to come off the line exactly where we want to, and then come up with any other details. So to do this, we can go down to the floor, go to the process level, begin to ask questions about process details. We don't want to engage the team or interview them about process problems or improvement ideas. It's our opportunity to go in, understand for ourselves, right? Be humble enough to go and observe before we start pontificating or, So this is what he's encouraging us to do. Go learn and see. Go to Gemba, right? Go see. The process steps are get to know the process by, again, defining the start and end points of the process. We're going to have a beginning process where we're putting springs in the board. We're going to come over here, we're going to test the board, right? What are the batch sizes? We'll look at how many pieces build up in the whip. How many pieces are we doing in batches, and where does the whip build up? So we're beginning to look at that, and we're going to be sketching a simple block diagram. Nothing fancy, just a starting point. We want to know how much does the process fluctuate. So we'll take 20 to 30 exit cycles off the line and just gather some information and see what kind of range we have, and we'll plot that in sort of a run chart. We ask ourselves, does each operator does his or her steps the same way each time? And then any other observations, either good or bad, just what do we see? Okay? So we're all going to have a chance to observe the buzz electronics factor here in a minute. Once we're done, we just render that into a simple block diagram. Again, it's just a straight line rendering of the process steps. Okay? Each process step, it's a workstation. It tells what's happening here. We show a little symbol, kind of like from our battery mapping. How many operators do we have? Where do we have work in process building? Do we have a little variation? What's the batch size? Whatever information. Nothing fancy, we just get started. We're processing exit cycles, how often the piece falls off the line. We're not looking at this initially, not the lead time. So no, how often these pieces drop off the line. The time between the coming off and the end of the next process. Not how long, but how often. We'll render that stuff into this chart. We've divided it into 2 kinds of time. One is the actual cycle time. So as you together as teams, we'll put you together. We're going to kind of have 3 teams. Again, big groups, so bear with us. But ultimately what you're trying to do is from the 20 or so cycles we look at, what's the total cycle time, right? And then somebody else can be looking at that, and then of that total cycle time, just do the math in your head. How many seconds was really value added where we were actually touching and building the product? The rest of that time is for other stuff like waiting or whatever. And then for each one of these cycles where you see something unique, just note an observation. You'll have a form that has round 1, you'll have a form that has round 2. So we'll have data for somebody that's watching springs, which would be the first step in the process, resistors, the next step in the process, another resistor, a diode, an LED, and a test. That's our initial starting point. We'll then dump that data into a simple run chart. It looks complicated, but it's not. We start with the grid. We put the scale in here. Where we know takt time, we'll lay that line in. Where we know our planned cycle time, we'll lay that line in. Once we've gathered our 20 to 30 cycle points, we'll just simply put the dots in, connect them, and then we step back. It's kind of like value stream mapping, where you see the Kaizen burst, the information jumps out at you when you know what you're reading. We're going to look at two things. We want to know what's the lowest repeatable. So this little white column right here says, you know, there's a cluster of dots right there. It's suggested maybe that's about the lowest repeatable. Again, it doesn't have to be perfect. But then also, what's the range? What's the high point and what's the low point? So when we walk by this chart, we begin to see the information jump out at us, and we can begin to see from this chart, are we in trouble? Yeah, we are, right? Our lowest repeatable, we can't even meet our planned cycle time, and our range is above our takt time. So again, it just tells us where to begin. Whoops, sorry. So again, stepwise, the first step again is lay the takt time and planned cycle time if you have them. Step 2, put in the dots, connect them. Step 3, just take a ruler, run it up and down until you see a cluster here. When you do that, that kind of becomes that lowest repeatable number. Okay? By finding that, we just move the ruler up and down. We draw that bar. Then we come over here, we calculate the plus and the minus, right? High point, low point. So here's a little formula. We want to know what percent of our cycles were above the highest planned cycle time and what percent were below. So the math is simple, meaning that we take the highest point, which would be that point up there, subtract the planned cycle time, and then divide all that by the planned cycle. That gives us that plus 100%, and multiply by 100. That gives us the percent above. Same thing for the lowest. We just take the lowest repeatable number here, subtract planned cycle time, divide it by planned cycle time, and we get the percent negative. So we get two pieces of information. Again, the fluctuation in the operator cycle, and we get the lowest repeatable time. Questions? And we'll fast. We're going to do this, so we'll have time to kind of flip through it. Here's a couple of examples. We got an operator X, maybe he or she worked in the first shift. Operator Y, maybe he or she worked in the second shift. So if we know our takt time and our planned cycle time, we lay that in. Here's a series of dots. Our lowest repeatable is down here. Our range is here. So what would you say about this person right here? Okay, right? If you come down here then, maybe it's the same operation, different people, different conditions, start to see planned cycle time and takt time, but whoops, you know, we got a little bit of a range situation here. So that information pops out and says, you know, maybe the first thing we need to do is just see if we can't run a stable process for our first experiment. We had standard work, don't we? We know how the line should run. But when we actually begin to gather the data, we begin to see that, you know, it's not what we thought. So again, how much?
Usually the second shift person is that person up top, the first shift person is that person on bottom. Really pisses first shift people off, that's the truth.
So,
They're usually slower, because they're the senior and they know better, and those night shift people don't know what they're doing. Night shift people usually try harder.
But the first shift people really are reworking all the stuff you messed up last night. So
okay.
I work on second shift.
Been there, done that, right?
But it does show us the difference, right? And then we have to kind of investigate as to why. So how much is too much fluctuation? Well, if we have too much fluctuation, it's really hard to make improvements, right? Kind of hit the moving target. So too much fluctuation, it's no improvement. Causes are always changing. We're not able to meet customer demands without overtime. We don't have that pace, that cadence, that rhythm. Sometimes we rush, sometimes we wait. It's really hard to develop anybody's skill sets. So, make sense? Okay, well, the process is not cycling within the desired limits. We're not able, then maybe that's the person we have to work on. Is your question? Okay. So here's an example. We took 20 exit cycles off the buzz. We put them up here in a run chart. Brandon's going to kind of take us through how the calculations start. Again, 20 samples. These were the actual cycle times that came off. We happen to know that buzz has a 12-second takt time and a 10.2-second planned cycle time. So to kind of look over there.
I'm glad Robert stood up and volunteered for a couple of hours.
All right.
It'd be so helpful. So what we do is we take the cycle times there, and this is total cycle time, and we're just connecting the dots. That's where it started. So first we plotted them. I'll put an X in each one of the spots. And so if you want to just go ahead and take it over here and continue to just connect the dots with the X's. Make sure not to skip one, because it's very easy to skip one. just wanted to show it on this chart. Basically, the operations you guys are gonna be working on have more of a step-by-step chart. So what Robert just did was basically sketch this out for me. And the lowest point on the map is, what, Robert? 6. So the lowest cycle time for this operation was right here at 6 seconds. The highest point here is at
I think if you turn it over, you can see
Okay.
it.
So this is the lowest point. This is the high point. Okay, so we have our highest and our lowest points, but we don't have our lowest repeatable. Now, if you'll flip back a couple slides if you don't mind, where it says do not use averages. We always get this question, I think it's a couple more, right there. Do not use averages, include all data points. The first thing you're going to want to do when you start timing this is you're going to do this, and you're going to do it, and all of a sudden, train wreck's going to happen, and it's going to be 57 seconds. And you're going to say, should I just exclude that? I mean, that was just an anomaly. We don't want to do that. There's a reason why that happened. It's usually a common cause variation, and we want to get back to the point of what caused that so it doesn't happen again. So don't exclude any data. The other thing is, it'd be real easy to come in here and say, okay, for our lowest repeatable, I'm going to use the average right there with the root and say 16 seconds. But is that striving for improvement? The next thing you're going to ask yourself when you're doing this is, what does repeatable mean? Okay, so I've got 6, as I slide my ruler, 9, oh, there's 10 twice. Do I want to set it at 10? Why wouldn't I want to set it at 10? I can't hear everyone.
There's 3 above you that are the same.
There's too many that's above it, right? So we want to keep moving up here until we get, oh, well, there's 12. Okay, there's 12. 1, 2, 3, 4. And we have 1, 2, 3, 4 below it. So out of 20 points, 12 and below happens 8 times out of 20. So now we're starting to get into kind of a repeatable pattern. You may go up a little bit higher and say, I'm going to split the difference because I see 15 repeats 3 times and then 14 there, so I might set it at 13 or 12. It's a subjective measurement, as Bill says. It's a place to start. Again, don't exclude data, don't use averages, and don't just pick the first 2 points that repeat. A good rule of thumb is keep sliding until you see it 3 or 4 times, or kind of eyeball between 4 to 6 data points and 4 to 6 data points. Because if I said 14, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 points. Over 50% of the points are around 14 within 1 second. So I would say that's okay. Another group might look at it and say, no, I'm a purist. I've got 4 points that repeat. 8 out of 20 of them are below it. I'm going to set it at 20.
And don't forget, the reasons why those ones are really high are probably due to those issues that we're going to build into the 15%.
Exactly. So what do you think, Robert? Where do you want to set this? We said 12, 15, 12? Okay. So we want to draw, first of all, a bar chart here up to 12. Little box that he talked about. Kind of hard to see, but I'll try to make it follow the line if I can. Okay, and we're going to say that the lowest repeat is 12 seconds. Okay? Now with your red marker, split to that right there. What we want to try and that's good right there, Bill. We want to try and create this bar between the lowest point and the highest point. We want to do it inside that. So we know our lowest point was at 6. So right over here, draw just a little red line at 6. and draw a line out here above the bar at 24, and just draw bars straight down through our graph right there. All the way down to 6, all the way down to 6. So what we've done here is we've kind of created that red bar inside of the blue bar. And what we think we can do is get to a process where 12 seconds is repeatable, but we've got variation up to 24 and down to 6. And what I usually like to write is 6 down here, and of course we've got 24 up there. Now we have to go through this calculation that's on slide 61. Highest variation is the highest point minus the planned cycle time divided by the planned cycle time. So we know our planned cycle time is 10.2. We got that from this calculation based off of our TAC. So we're going to write 24 in that gray box. Now, and now's the time where everybody else gets out their iPhones or Samsungs and their calculators.
Good.
He says the math is too complex for him to handle it inside of his ears, so help him out there. 24 minus 10.2 divided by 10.2. Make sure you do your order of operations correctly. Times 100 to give a percent variation. Should get around 135%. 135% there.
That'd be a plus, right?
Yep, not plus size. There. Yep. So what is that number telling me? The highest variation of 24 seconds is 135% of planned cycle time, right? This green dotted line going across here. What would be 100% of it? It's 10.2. So 100% would be another 10.2, which would be 20.4. And then about another third more would get me up to 24 seconds. So I'm 135%, or I'm double plus a third higher than what I want to be on my planned cycle time. Does that make sense? And that calculation is? Okay, let's do the low. No? Okay. If my lowest, or if my planned cycle time was 10, and I was operating at 100% above that, I would be at 20.4. This calculation is telling me I'm also another 35% above that. I'm 135% above my planned cycle time. So I'm another 35%, so 35% of that's about 3.5 seconds. So up to 20.4 plus 3.5 seconds gives me about 24 seconds. So let's use blue now. Buzz likes his colors.
And you guys, the formula is on page 53. It's a little, there's a few slides that we're adding.
And we're going to say our lowest point here is 6. So we're going to put 6 in there. Minus 10.2. And then divide that by 10.2. And we get negative 41%. So what does that tell us? That at one point, when we were running the operation, we were able to run it 41% below our planned cycle time. Again, our planned cycle time is roughly 10 seconds. What's 40% of 10? 6 seconds. Okay? So we know we can beat planned cycle time by 41%. In fact, we can beat it by everything that's below this green line. Now we want to take the average cycle time, so we want to take up the sum of the total cycle time, so we want to add up all of these seconds. Can you go back to the chart where that's at? Where that is at? And we want to add up all of those seconds.
If we did, it would add up to, what was those up, and when that number comes, then you can divide it by,
Divided by 20, the total number of units. We're spending a lot of time on this just so because we're going to go through this exercise several times today to capture the current conditions.
14.
That was dividing it by 20? Okay. So the total seconds, did anybody get that?
296.
296. Divided by 20 total units that we ran, gave us 14.8. So again, that's about the average of all of those, put my ruler in there. And if I want to calculate my daily output, my available time I said was 27,000 seconds. I give my people 30 minutes of break time. So for purposes of daily output, 27,000 seconds divided by 14.8. About 14.8 seconds per unit there. 27,000 divided by 14.8. Said if we ran that 20-second block continually for 8 hours, we would get how many hours in today? 1824. So 1,824. And what does Buzz want? What makes him happy? 2250. So I'm about 25% away from that, right? Hence, I'm running 2 hours of overtime. So we didn't just make all this up. Well, we did make it all up, but we made it up.
Quick question that, I know a lot of us in the room, we're doing linear production lines, where like I said, the attack time on a bottle is like below a second. Is there any rule of thumb that you've seen from your experience? Do you use cases in this case, or pallets?
And use cases with pallets typically, that's my personal opinion. Hank, I don't know, you maybe a little more bottle processing, but
Yeah, I think some of that, I probably use something like that. My question would kind of be, if you're looking at that line, going back to what should be your target condition? And maybe tack time, might be one of your targets out there. But is that maybe what we should or shouldn't be working on?
I know the key for me is we've always looked at the number of units per minute, so our metric is time-based. So we really feel like how the case cycle time and the pallet cycle time.
And there's variation in that?
Yeah, to find variation.
Yeah, and, that sounds like that would be one of your target conditions to use it like that.
I think in linear production where you have, a lot of times you have set line speeds. And so you're not going to see that you go over that as much from, your beginning cycle. Now you might have add-on areas where it might spike, but that's what Chad and I was just talking about for our world. A lot of times when we're in areas where we're looking at particular machines, especially if you have add-ons or rework type situations, you've got to know what the tack time of is that machine or your carton supply, film supply, whatever case supply it might be. And you've got to know that there's only a certain amount that particular area's cycle time can handle. So, whether it's bottles of Clorox or Little Debbie's in a box, if your machine above that's supplying you cases, cartons, whatever, is only capable of 60 cycles times however many units you're putting in there, adding 3 people to add on is going to get you nowhere. So I think for a lot of management in that world, it's almost knowing more of the cycle times of different areas of your linear production.
you really brought up a key point. We're going to see how we now have to also look at machine capability. And if we can't make it, that's where we would go with after experiment. So we can get back to yours, bottles per second, or cases or cartons, pallets. And,
let's give Rob a thunder of applause. We volunteer.
He gets more out of it than we do.
I don't believe a word he said.
all right, so what we're going to do is we're going to come up with an obstacles parking lot. We use this document here. As you as you look at the process, you'll be writing down your obstacles, knowing full well, maybe not gonna work on all of them, but as you see things, we wanna so note them. So we got the form here, you also have it on the wall over there. So again, to Gina's point, and the conversation we just had, we next need to look at our equipment. Can our equipment meet our requirements? So we begin to look at it, same chart, we lay in tack time, we lay in planned cycle time, and then we lay in our different machining centers, okay? We've got number 10, number 40, et cetera, right? So we've got the machine cycle time plus its load and unload time. And if we know our planned cycle time here, we got number 90 bumping up against it, we got an issue. So just like we did with our tack time and our planned cycle time, we came down a little bit. We're doing the same thing with our machines for the same reason. We're saying, okay, we want our machines to cycle within 90% of planned cycle time, get that little safety factor. So very timely comment about machining. This is an important check for the process that has automated equipment. Let's talk about that. If it can't cycle fast enough, then that's where we would go to begin. Okay. So a little more about, I apologize for this. We went from a PowerPoint to a PDF and back to a PowerPoint. Some of this stuff got a little bit out of whack. So, this guideline applies to only automated equipment. We're not talking about hand tools and things like that. The basic point in looking at the cycle times for machines, it's okay for a machine to finish cycling and wait for an operator, but not the time. And the machine really only needs to cycle once during that, cycle once per tack time. If we look at total machine cycle time, we want it to be no greater than 90% of our planned cycle time. Again, just a starting point. Right? And again, it applies to machines, not to operators. So if a machine utilization is too high, then workstations become close coupled, and we got small cycle variations that telegraph up and down the stream. And that, again, contributes to instability and leads to buffer. So if machine utilization is too high, the workstations do that. If machine utilization is too high, then the operators will have to wait for a machine to finish, and that interrupts their pattern of behavior as well. So again, the fastest planned cycle time that a line can run is really take that longest machine cycle time, divide it by 90, and that would be the fastest that the planned cycle time could be. And if it's not within your guidelines, then again, that's where you can go first. Questions, comments, suggestions? Okay with that? This means yes, this means no.
Those say that guideline is only for automated machines, not operator-assisted machines.
I think the same deal, right? If it can't cycle once within tack, then we have to go there. So, again, in this case, we've got the machine cycle time, and then actually probably the operator load and unload. Okay, so again, how do we chart it? First step simply is lane attack, planned cycle time, 90%. We come in and put in the various machine centers, listed at the bottom. Add in the pure machine time as we understand it. Add in the load, unload as we understand it. And we would probably see where the problems are. So by adding the sum of the pure machine cycle time and the unload cycle time, that really equates to the actual total machine cycle time. A little fast, okay with this? Yes. All right. Once we've got these three things, we go to kind of look at how many operators do we really actually need to have. We know that in our value stream mapping conversation, we took the sum of the cycle time divided by tack time, kind of get a benchmark this about how many people we need to have. So we're going to kind of do something similar with our planned cycle time. What we do here is we look at the operator task, we summarize, instead of the sum of the cycle time, we're going to summarize the lowest repeatable. We're going to come up with a number. So we add up all of this information here. We know what our planned cycle time is. So we're going to take this lowest repeatable sum divided by planned cycle time, and that will tell us about how many folks we should have on the line, 3.2 in this case. So again, if we remember from value stream mapping, the sum of the cycle time, the value add time, divided by the tack time, suggests how many people we should have. In this case, what we're doing, we're taking the lowest repeatable sum divided by planned cycle time, and still coming up with a starting point. You know, this is maybe if we've got 4 people there or 5, then we kind of know this is what we're trying to look for. We're trying to get down to, say, 3 people. If we observe consistent wait time, we want to kind of back that out so that we can get closer to the actual task time. So why is it okay to use this? Again, starting point. This is the beginning. It's acceptable, especially if you're going to do a lot of these daily PDCA cycles. So just begin. The initial times don't have to be exact. We'll notice things and we'll become more accurate. We can adjust along the way. We're not trying to set a standard. We're capturing data, facts, information and data, so that we can do what? Set the target condition. That's the whole purpose of this exercise. We'll learn more about the process, and then incorporate it, and we'll get more detailed information along the way. Last step then is to measure the outcome. What are we looking for? We might graph output per shift, or maybe overtime, anything else that affects the outcome. Here's an example, output per shift, simple graph, and here's overtime. That's what we want to measure, so we know which direction we're going in. We can bring in additional metrics, productivity, cost, labor, whatever. Kind of a little thing about terminology, we kind of look at process metrics versus outcome metrics. Outcome metrics kind of indicate how the process or the system is performing over a period of time. It has to do with things like lead time or output per hour, cost, labor, productivity. This is kind of like data driven, something we measure. Again, it might be a scrap rate. Over here in the process metric, it occurs approximately the same time as the condition that it's signified. So a good example is the work that each cycle takes. So again, data versus facts, something you observe. An example might be the actual occurrence of scrap. You'll see this form up on the board. It is what you would utilize at your Kata board. So as we begin to gather information, we start looking at this. This is the current condition, target condition form. This is the point of conversation between the coach and the learner. Again, it's so freeing to have all that information there. The learner knows the coach is going to come. They're going to use the 5 questions. 15 minutes later, it's done. We're back on track. Okay? Every day, we're just talking about this important issue. Do the 5 steps. 1, task time to complete. 2, current operating pattern. What does it look like? 3, reconcile equipment. 4, how many people do we need? What outcome metrics? That's the generic side of it. Specifically for a discrete widget manufacturing, we're looking at takt time, planned cycle time, shifts. We look at the process steps. We would show the block diagram. Obviously, we can't stick it in that little spot there, but we would have it available to bring into the discussion. Where we have batch sizes or WIP, operators, and you don't have to exactly follow this. It's whatever it takes you all, whatever you need to describe that current condition. Once we have that current condition, the data and everything is there by a certain date, we then can talk about what target conditions. Some of these things we'll bring across, they'll be the same. Our takt time is probably going to be the same. Our planned cycle time will probably be the same. But maybe we want to reduce batches or reduce the numbers of operators, whatever. Again, it brings all this together, sticks it up on the board, and the beauty is the coach and the learner point to the data and talk. It's not one of these back and forth, right? We talked about the most feared words, I don't know. It's okay for the learner to say, I don't know, because at that point, the coach recognizes hey, that's where we need to go. Okay, so as an example of it, again, the 5 steps. The data are all up here. We've gathered it all. We've laid in how the machines look. We've laid in how the operators look. At a glance, we can walk by this Kata board. This jumps right out at us. Those of us who understand how to read them now will know where the team is and how they're progressing.
Bill?
Yes, sir.
You have guidelines like 90% for equipment and things like that. You didn't come up with a guideline for operators. Is there any?
Well, again, the calculation for operators is this formula right here.
I have the calculation, but if that came out 3.9, is that 4 people or is that 5 people?
Yeah, I mean,
a lot of people use 80%.
Very good question. Again, you know, what are we looking for? What could we do? What could we do? I guess the answer would be, if it's 3.9, okay, so we got 4. If we can tolerate that, fine. if we need to only run with 3, what do we need to do to take out 0.9 of a person? And that might be the challenge. So it's, how would you answer that? What do y'all think? You got 3.9, we just say, okay, we can tolerate that. But if it's 3.5, would you go to 4 or would you go to 3? You know. Again, it's just an indication of how many people you have in your process.
Yeah, you know, it is that's the, right now, you're just trying to understand the current condition. And then your question would be, what should you do in your target condition?
Right.
And that would, like Bill said, that would be your decision. 3.9, you may have a target condition of 3 operators, right? And it may be difficult to get there, or it may be very hard to get there, you know, but you may have that as your target.
Okay, so lunch is coming in, I think, 11:30, is that right?
11:30 is right.
We're gonna do our very best to run at least round 1 of the simulation, so we're getting real close to the end of the slides here, and then what we're gonna do is we're gonna kind of break into groups, and we'll kind of do a simulation, and hopefully as close to 11:30 we'll be done, and we actually have to stop and go. So this is the kind of board, I'm gonna be bringing things together. You identify what's the process you're looking at, what is the challenge statement. Again, those of us who went to the tours, we saw a lot of visuals out there, didn't we? This is really important, and it's all right there. The coach and the learner come and they talk to the stuff, not back and forth against each other. Process focus, the challenge, what's the target condition information, what's the current condition information. We'll talk about PDCA cycle records. What were they? We'll record all that information. It's all right there. What obstacles do we see? And setting up that board in that format kind of gives us that starting point. What Rother and Cover with Toyota is that they don't do this. It's just natural to them. So he's encouraging us to follow the steps. Right? So go slow to grow fast. We want to do our due diligence. Eventually it'll become second nature to us. We won't need to go through this part of the process.
Yeah, and you can go back, Bill, even on that one, like Bill says, this is kind of where it is, right? You know what you're focused on in the process, your challenge, long-term out there. You're gonna break it down into your target condition. Here's your current condition, that's a gap. There's gonna be obstacles, right, to the gap, and then you're gonna PDCA off one of those obstacles. So that's where we're going with this chart, that's where it kind of relates, fits all together.
I see a little deer in the headlights. Look, I felt the same way when I was doing it, but are we kind of on track? Everybody kind of see this? You know, again, you have to go back and look at it, study it, read it a little bit. It'll make sense to you. But again, we apologize for the turbo here, but we are trying to be mindful of going through all this. So go to Rother's website, look at the forms. They're all available. Reflect, think about what we talked about, and it will make sense.
You can go back to the same point, you know, you all talked on gaps, just to start with, a lot of sustaining, right? Fair statement, and everybody would struggle with it too out there.